Hi everyone, I'm Shrestha from the Neurofest lab at the University of Calgary, and I'm going to talk about the ultrasound imaging of materials for estimation of its acoustic properties. So looking at HIFU applications for transcranial focused ultrasound, we know that the skull aberrates the ultrasound. While it was considered that skull would not be an issue with low intensity focused ultrasound, it has been found that that is not the case. We can see in Figure 1, a study conducted by Dr. Trebley, that the focus is not precise and the shape is also distorted due to the skull. Numerical simulations on ultrasound propagation by Lagon group show multiple lobes and significant distortions present in the skull as shown in Figure 3. Clinical studies targeting the visual cortex show deviations from the intended target. We do know that CT and numerical simulations can refocus the ultrasound. However, neurostimulation studies are done on healthy volunteers, and exposing them to radiation would not be possible. So, the goal here is to estimate subject-specific skull acoustic properties for refocusing using a phased array transducer. Here we present a method for estimating the acoustic properties of a layered material by imaging the material with ultrasound. We use variable focusing technique to locate the further edge of the material from the transducer by electronically moving the focus through the material. The ultrasound echo from the further edge of the skull is at its maximum when ultrasound is focused at the furthest edge of the material. We use the focus distance from the transducer to the further edge of the material and the ultrasound echo of the material to estimate its acoustic properties. The equations on the right are used to estimate the speed of sound and the thickness of the material. We use differences in geometry between the free water conditions and with the material and the ultrasound echo principles for the estimation. So to test our method, we used 1 MHz 32 element linear array by sonic concept. We believe that 1 MHz broadband array will provide the necessary signal to noise ratio to image the skull for estimation. We tested the method on 2 plastic phantoms, polycarbonate and high density polyethylene, and also a skull phantom. The experiment was performed in an acoustic tank with degassed and deionized water. The thickness of the plastic phantom and the skull phantoms were also calculated using either a caliper or CT, while needle hydrophone was used to calculate the speed of sound of the phantoms. Here we see the results of the test on the phantoms. Figure 5 shows an ultrasound echo from the skull phantoms where the focus distance to the furthest edge was determined to be 47 millimeters. The two peaks indicate the nearest and the furthest edge of the phantom. The table at the bottom of the slide shows the estimated speed of sound and thickness with their corresponding caliper or CT and hydrophone measurements. The error in the estimation for the plastic phantoms were calculated to be about 1.4% for thickness and 3.5% for the speed of sound, while the error for skull phantom were calculated to be 20% for thickness and 15% for the speed of sound. Next, we'll use the estimated acoustic properties to refocus the ultrasound using a 128 element low intensity focused ultrasound phased array, which can be seen on Figure 6. This method will enable neurostimulation of cortical and subcortical targets in human volunteers with no radiation exposure and with real-time aberration correction.